So question number 3. An alkyl halide X having molecular formula C6H13Cl reacts with CH3 thrice COK to form two isomeric alkenes Y and Z of molecular formula C6H12. Both these alkenes give 2,3-dimethyl butane on halogenation. Find halide. So we have one reaction which saying both the isomeric alkenes Y and Z they give 2,3-dimethyl butane on halogenation. So we have to find this particular halide. How do we go about this?
Looking into the format of the question, we can see that this question is of, we had a substrate A, it went under some reaction, we got B, it again went into some reaction, and then we got C. So whenever we have such questions, we must always start from what information is given to us. So moving ahead, we know that C is actually 2,3-dimethyl butane.
Yeah, exactly.
So how do we get C? We got C when we actually added a pi bond to when we reduced a pi bond from B, because the statement says that a 2,3-dimethyl butane was obtained
on halogenation.
halogenation. Okay. So what are the possible ways of adding a pi bond into this question? It can be either this way or this way.
Right.
Okay.
Exactly.
So we can say that these are the two possible products of B. Noting that we must remember one thing, that this is called as Hoffman alkene and this is called as Zaitsev alkene.
Okay, and okay, why? How do we differentiate between these?
When the pi bond is between over here, it has maximum number of carbons as the substitutes. The number of alpha hydrogen, which is, these are the alpha carbons,
Maximum.
are maximum. So
Okay.
more is the hyperconjugation and more is the stable one.
Okay, and
so
Hoffman is otherwise.
the Hoffman is otherwise. So we can say that on a general basis, Zaitsev alkene is more stable than an Hoffman alkene.
Right, okay.
Okay. So moving ahead, we have actually arrived to B. So now, looking into the question, we have to find out what is A. So A is an alkyl halide having molecular formula C6H13Cl. So
Right.
how do we find out what the structure will be? So first step we check is out DOU, which means degree of unsaturation.
Okay.
Okay, so how do we calculate DOU? To calculate DOU, and if the molecular formula has an halogen, what we do is remove all the halogen atoms and add equivalent hydrogen atoms. So this
Okay.
product becomes C6H14. And to calculate DOU, the formula is 2C minus H plus 2 whole divided by 2. So it comes out to be 0. So it is an unsaturated alkene.
Right.
Okay, so moving ahead, what are the possible ways of solving this question? So we have two alkene. We concluded that we have one Hoffman alkene and the other was Zaitsev alkene.
Right.
So now this went under elimination. So we have to add halogens to get the alkene A.
Exactly.
Okay, so we will be adding chlorine. So what are the possible ways of adding HCl over here? So it can be either it adds to this one or it adds to this one.
Okay, yeah.
And in this case there is only one product possible, which is this one. Because either way you attach the product to obtain will be in symmetrical and the very same thing. Okay.
True.
So we can say that these are the possible products. But we must notice that these are the common ones. Okay.
In the sense?
And if we actually start with this product as an alkene A, then we won't arrive to this product.
Okay.
Okay, so this has to be rejected.
Right.
So our answer is this one. So this is our alkene A.
Right, so this was basically the halide which I had to find.
Exactly.
Right, brilliant. So what do we have here? We had to find the halide X, and our question was in the form of A reacts to give B, B becomes C, and we had to find A, and we found B immediately. and then we found C. My bad, we found C immediately, and then we found B based on the fact that there are two possibilities: a Hoffman product and a Zaitsev product. And then we went through two different reactants for A in each case, and we eliminated one case of A based on the fact that it will not give this as its product, which was this. We eliminated this product. So hence the final answer, or the alkyl halide which they asked for, was this particular product. So this was question number 4. Question 4. So basically there is this compound where there's Cl, there's a phenyl group, there's ETO, and there's another phenyl group which basically, when put in NI and acetone, how does this exactly react? We need to find the products, we need to figure out how it reacts and what reactions will happen, why it happens. So fine, I'm guessing acetone here is the medium, and NaI will also be the will be a reactant.
Yeah, exactly. NaI is a reactant, whereas acetone is a medium. Acetone is a polar solvent, and so that NaI can act as an nucleophile over here. So we can, looking into the NaI and acetone, we can say that it will be an SN2 reaction.
SN2, yes.
Okay.
Why so exactly?
Because it's a strong nucleophile in a polar solvent.
Okay.
So it will
give
us an SN2 reaction.
So it will be a single step reaction.
Exactly. So now first we have to look into what a nucleophile will substitute. So we have two possibilities over here. One is ETO minus and the other is Cl
minus.
So knowing the fact that Cl minus is a better living group than ETO minus, we can say that NaI will be attacking on this carbon.
Right.
And Cl minus will get removed. Okay,
fine.
So, but there is one thing that we should remember is neighboring group participation effect.
Okay, neighboring group participation effect. Okay, so what exactly is this?
It states that if the attack is on this carbon, and if I have an other nucleophile in this one, so this carbon will experience retention of configuration.
Right.
Okay. Unlike SN2, in which usually happen is that inversion of configuration. SN2 reactions are usually followed by inversion of configuration. But if we have a nucleophile attached to an to the adjacent carbon, then it always will be a retention of configuration.
Okay.
This is the main thing that we should keep in mind. So moving ahead, we can see that I minus will attack. As a result, the product that we get will be
ETOH and TH in the volume. Yeah.
pH. With retention of configuration. Had it been only a SN2 reaction, the product that we would have got will be an inversion of configuration.
Right.
But due to neighboring group participation, we get this product and we don't get this product at all.
Exactly.
This was the main crux of the question.
Okay. So, right. So what we needed to find was the product, right? And yeah, this was one important thing which we needed to remember: the neighboring group participation effect. So what happens over here is that when so finally, is this the product which we need, which is necessary for us to?
This is the product that we usually get during an SN2 reaction.
This is okay.
But since due to neighboring group participation effect, that when a nucleophile under the nucleophile is present in the adjacent carbon, then there is always retention of configuration.
Okay. So retention of configuration gives us this product.
Exactly.
Right. So this. We have to remember that this we might usually go wrong saying that this might be the product. We have to remember that neighboring group participation effect causes pH minus, causes this retention, and this should be the right answer. And I'm pretty sure this also would be an option in the question. So yeah, that would be question number 4. So in question number 5, we have a cyclohexene ring, which is then reacted in NBS, gives A, and then in magnesium ether it gives B, and then CH3CN and H3O it gives C. So yeah, we need to find out what A is, what B is, and what C is. So let's go step by step. How does NBS? What exactly is NBS, and how does it react?
NBS is N-bromosuccinamide.
Okay.
NBS performs free radical substitution reaction.
Okay.
And attaches Br at a allylic position. That is this one or this one. Allylic position is the one which is the one adjacent to the carbon having pi bond.
Right. Perfect.
Okay. So NBS. So our first step will be when cyclohexene reacts with NBS, it gives via free radical substitution reaction. It gives this product.
Fine.
Okay. So this is A.
Yes.
So moving ahead, the reaction will take place with Mg ether. Okay. So one thing that that is very important is when alkyl halide reacts with Mg and ether, it gives RMGX, which is a very popular compound called as the Grignard reagent. When Grignard reagent reacts with, like, let us see in this example itself.
Right.
When this compound reacts with Mg ether, it gives us another Grignard reagent.
Right.
Which is
MgBr, is it?
MgBr.
Right.
So this is a product B.
Okay. So this isn't a stable compound as such, I believe.
This is not exactly a stable compound, but it's a very good nucleophile.
Right.
Because because magnesium is there's a positive charge and there's a negative charge over here,
Exactly.
so it acts as a very good nucleophile.
Fine.
Okay, so moving ahead, this compound will react with CH3CN in presence of H3O plus.
Right.
So the role of H3O plus is acidic hydrolysis, which will come when this reacts with this first. Okay. So moving ahead, CH3 C triple bond in. The negative charge will attack over here, and this pi bond density will shift to nitrogen.
Okay.
So we get
CN. Okay.
Okay. And when this undergoes acidic hydrolysis, we get
Okay. As well as we get what is the other side product which comes out?
that's a byproduct which need not be considered at all.
Okay.
Because whenever we are reacting Grignard reagent, we should only be concerned with the main product. Byproducts are not at all necessary.
Right. So there'll be multiple byproducts which aren't that prominent at all.
Exactly.
Fine.
The concentration will be very less.
Okay. So what we had here was we had this particular cyclohexene ring, and this ring, when reacted with NBS, gave us so the Br group attacks on the allylic sites, which are this and this, which are adjacent to the carbon which has a pi bond. So we got this particular product, and this is A. And when this reacts in Mg ether, we get something called a Grignard's reagent. So this Grignard reagent is when we get this particular compound, the same cyclohexene ring, and instead of Br it will be MgBr. So this is product B, and now all we needed to do was find product C. So in CH3CN and H3O plus, what happens is this particular MgBr will shift towards it, as it will align itself like this. So this product in water, or H3O plus to be in fact, we get this particular product, which is CH3 C double bond O, and then a cyclohexene ring. So basically what happens here is the double bond N MgBr is replaced by a double bond O. So this is Grignard's reaction,
This is acidic hydrolysis.
Exactly. This is acidic hydrolysis for.
And the previous step was Grignard reagent.
Okay, so this is a Grignard's reagent going through acid hydrolysis.
Exactly.
Fine, perfect. So this particular compound right here is our final product, which can be called C. So we have all the three products, and yes, all we need to remember is a few reagents like Mg ether. What will happen if a particular compound with a pi bond is reacted with NBS, with Mg ether, and concepts like acid hydrolysis. So yeah, this would be question number 5. So in question 6, there's this benzene ring, and there's a hydroxyl group, and there's another carbon chain attached over here. This particular compound, when it is put in excess of H plus, what is going to happen? What is the reaction which is going to happen?
We know that H plus is an electrophile.
Mm-hmm.
Okay, so we have two nucleophiles over here. One is OH, and the second is the alkene bond over here.
Yes.
So either of them will attack H plus.
Yes.
So we have to first select which one of them will.
True.
One thing that we must notice that the lone pairs in oxygen will be involved in resonance with the benzene ring.
Okay, so
Okay,
it will be adding to the stability.
Yeah. So the point of attack will be pi bond of this alkene.
Mm-hmm.
Okay. So moving to the next step, the pi bonds attacks H plus, and we get this product.
OH benzene ring.
2 degree cation was more stable than 1 degree cation.
Okay.
That's why the positive charge comes over here rather than over here.
Perfect.
Now we know that this positive charge is very less stable.
Mm-hmm.
So the weaker nucleophile will attack the positive charge.
Mm-hmm.
Okay, so the next step moves on to though these lone pairs were involved in resonance. This is a very fast step because because of the formation of 6-member cyclohexane ring. Whenever there is a formation of 5, 6 or 7-member cyclic ring, it's a very fast step because it's very spontaneous towards the product side.
Right, because the product is pretty stable.
Exactly.
Mm-hmm.
Okay, so now the next step will be these lone pairs go to oxygen because it's more electronegative, it attracts, and H plus is again released.
Fine.
Okay, so we are left with, and our H plus is regained back. So we can see that the H plus is being acting as the catalyst over here, and this is our final product.
Brilliant. So fine. So we have to think of two things over here. One is that H plus is a catalyst. So what this does is there are two ways in which the H plus can react with this particular compound. One is with OH, and one is this alkene. But then this OH, the lone pair on O, the oxygen, will be in resonance with the benzene rings, which increases the stability of the ring. So it would prefer the alkene group, and then while it prefers the alkene group, the positive charge goes on this particular carbon atom and not this particular carbon atom, because we have to remember that 2 degree carbocations are much stabler than 1 degree carbocation. 2 degree carbocation, as in there are 2 carbon adjacent to that particular carbon, whereas this is a corner carbon cation. So after this we cannot stop at this particular situation, because we get a much more stable product in a couple of more steps. So what happens here is that we get this as our final product when H plus leaves and gets back over here and behaves as a catalyst. So our final product being this particular a double ring structure with oxygen in them is pretty stable. So we need to remember another fact, that when there are other cyclic rings which are being formed, 5-member, 6-member or 7-member rings, it happens instantaneously, because they are pretty, the compound or the product which is formed is much stabler than the previous products in the previous couple of steps. So yes, this was question number 6.